So I already talked about the pendulum. I'm just going to show you a diagram that I've made. So at the highest point, point A, the pendulum is momentarily motionless. All the energy in the pendulum is gravitational potential energy, and there's no kinetic energy. At the lowest point, point D, the pendulum has its greatest speed. All the energy in the pendulum is kinetic energy, and there's no gravitational potential energy. However, the total energy is constant at the function of time. In a simple pendulum with no friction, mechanical energy is conserved. Total mechanical energy is a combination of kinetic energy and gravitational potential energy. Linda will be talking about this later. As the pendulum swings back and forth, there's a constant exchange between kinetic and gravitational potential energy, as you see in the diagram. As the mass above loses height / gravitational potential energy, you gain speed and even kinetic energy. Same goes when the mass travels up. As you gain height and even e.g., you lose speed / ek. Now that Linda and I have taught 3 concepts, we should go ahead and solve a sample problem. So 2 children race to see who would win first. The first child rides on a flat road, while the second child rides on a road that's flat at first, but starts off with a 5-meter height, then declines, and then flattens out at the end. If their masses are both 10 kilograms, and they start off with 10 meters per second, who will win the race first?
For the second rider, since there is a height and a speed at the top, to find the total amount of energy, we have to find the Eg and Ek to find the total energy at the top. Tarj will be finding Ek, and I will be finding Eg. I started off with the formula Eg equals mgh. I subbed in 10 kilograms for the mass and subbed in 9.81 meters per second squared for gravity. I then subbed in 5 meters for the height compared to the bottom, and therefore the second child possesses a gravitational potential energy of 491 joules.
We now have the gravitational potential energy in the beginning for the second child, which is what Linda calculated, and she got 490.5 joules. We also know that the total energy equals to gravitational potential energy and kinetic energy. We already have gravitational potential energy, but now we need kinetic energy. So Ek equals 1.5 mass times velocity squared. We can plug in the values for mass and initial velocity. We now get Ek equals 1.5 multiplied by 10 kilograms multiplied by 10 meters per second squared, which now equals to 500 joules. We can add the gravitational potential energy and the kinetic energy, and we can get the total energy of 990.5 joules. Now at point A, which is where the child starts to decline, is when the speed starts to increase. This is where gravitational potential energy is being converted to kinetic energy. Knowing this, at point B is when the child will experience the maximum speed possible, and this is where gravitational potential energy is 0, and the only energy capable is kinetic energy. Now we can take 990.5 joules equal to 1.5 mass times velocity squared. Now we already know mass, so we can just solve for speed. So 990.5 multiplied by 2 divided by 10 kilograms, then we can square root the number, and this will give us a speed of 14.1 meters per second.
For the first child, when we subbed in the values in the equation, we found that Eg was actually 0 because there was no height. So therefore, the first child's gravitational potential energy is 0.
We can now calculate the first child's total energy. The only energy that is capable is kinetic energy. We can now calculate the total energy that the child has. So Ek equals 1.5 times 10 times 10 squared. This is resulting at 500 joules. Knowing that the second child has greater speed and more energy, we can conclude that the second child will be winning the race. The second child benefits due to him having more speed because he starts off with 5 meters of height. So as he declines in height, he'll be converting gravitational potential energy to kinetic energy, which will result of him having more speed. So throughout the lab, Linda and I kept the mass and the length of the string the same. My job was to see how speed affects kinetic energy and how that relates to the height. We calculated 5 points throughout the lab, and this includes extreme points such as 40 degrees to the left and right, the halfway points such as 20 degrees to the left and right, and last we calculated energy at the equilibrium, such as 0 degrees, which is in the middle. Now before I show you how I got these numbers, we need to know that the whole system always has the same amount of energy, meaning the energy that you start with is the energy that you end with. So you never lose energy and you never gain energy. It always stays the same. In other terms, energy is being converted from gravitational potential energy to kinetic energy, and this is vice versa. So when your gravitational potential energy is decreasing, your kinetic energy is increasing. So when your gravitational potential energy is increasing, your kinetic energy decreasing. But the total energy always remains the same throughout the whole system. You can see this with the image above. The main points which Linda will be covering is height. We already know that the total energy in the system is 2.4 joules, and this is because this is at the extreme points where the only energy capable is gravitational potential energy. Now at angle 0, we know that there's no height, and the only energy capable is kinetic energy. So we know that the total energy equals to kinetic energy. We can get 2.4 joules and have that equal to 1.5 mass times velocity squared. Multiply 2 by 2.4 and divide that by the mass, which is 0.1 kg, and square root that number, and then we get the maximum velocity as 6.84 meters per second. You can see from the table that when there's less height, you have more speed. We can relate this since when there's more speed in the system, there's more kinetic energy. And this is vice versa. So when there's less speed in the system, there's less kinetic energy. And this is because speed plays a major role since speed is being squared in the formula, such as Ek equals 1.5 mass times velocity squared. So when your speed is being doubled, your kinetic energy quadrupled.
I will now be talking about gravitational potential energy. Gravitational potential energy, or EG, is the potential energy associated with gravitational force because work is required to elevate objects against Earth's gravity. This means that it is energy due to location. So there has to be some kind of height, and since height is relative, that means there must be a reference point, and it also needs mass. Gravitational potential energy is used to find the energy stored in an object at a certain height. For example, if you take a look at the picture, my light has a height above the ground because it's dangling from the ceiling and is very heavy. But if my light were to fall, gravity will do work on it. Have you ever been on a roller coaster and did you realize how it always has to go up before it speeds downward? This is because the roller coaster gains height with the intention of losing it, converting its EG into EK. Essentially, this means that we're trading off height for an increased speed, and we all know the best part of the ride is the fastest part.
For safety precautions, do not do this at home. So, if Martutu is 5 kilograms and you bring him to the ceiling, his gravitational potential energy will be higher in relation to the floor than if you bring him down here on top of this chair. This is because the height on top of the ceiling is higher than where he is right now. Also, in the same circumstance, if me and Martutu shared the same height, since I have a bigger mass than Martutu, this means my EG will be bigger than Martutu's. And since this is Martutu's highest point of gravitational potential energy, if I whip him on the floor right here, since he is now on the floor, what does this mean? This means that since he has no more height, gravity cannot do any more work on him, which means he has no more EG.
If you look at the diagram here, work done at position A is equal to FAD cos theta. Since the mass will be falling, the downward force acting on it would be Fg, so we can replace the Fa in this equation with Fg. And if we look back at the equation, displacement is really just the height, so we can replace the displacement with height as well. As for theta, the angle between Fg and h is 0, because as Sona mentioned before, since the forces are parallel to each other, theta would be 0. And cos 0, as shown in this calculator, is equal to 1, so we do not have to include that because multiplying by 1 would not change any part of the equation. Then if we continue further, Fg is equal to mass times gravity, so we can replace Fg with mg, and there you have it. The derived formula for gravitational potential energy is Eg equals mgh. So using what we know, this formula can therefore only be used when there is a height or if the object is falling. And now unit analysis. So, first off, we have to know that gravitational potential energy is measured in joules, and then mass for the mgh is measured in kilograms. Acceleration due to gravity is measured in meters per second squared, and then the change in height from a reference point is measured in meters. Let's take a look at the equation and analyze the units. The equation is Eg equals mgh, and Eg is measured in joules. So it's 1 joule equals mass times acceleration times height. 1 joule equals 1 kilogram times meters per second squared times meters. And then 1 joule equals 1 kilogram times meters squared per second squared. And another way of saying a joule is this,
proving that Eg is measured in joules.
Now the best place to look at how energy is converted from potential to kinetic energy is in a pendulum, but since Tarj has already talked about that, my job is to further explain the role of gravitational potential energy in the pendulum. And so if I hold a pendulum at one side and do not let it go, it has a certain amount of gravitational potential energy. When I let it go, the pendulum will swing back and forth. If we assume that there is no air resistance, the pendulum will always return to the same maximum height at both of its extreme positions. It will never go higher or lower and will not stop moving. When the pendulum is at the top of its swing, or the extreme position, it stops moving for a brief moment at its turning point, meaning it is at its maximum height. And when there is maximum height, there is max Eg. When it swings back down to the equilibrium position, the potential energy becomes zero, because gravity cannot pull it down anymore. Since there is no height for it to lose, Eg cannot get lower than that. When the pendulum is swinging in between the equilibrium and extreme positions, there is both Eg and Ek because there is still some height, but not as much as it had when it first dropped. So let's read the sample problem. A 10 kilogram textbook is sitting on a 1.2 meter table. If the book is lifted 0.8 meters above the table, how much gravitational potential energy does it have? A, with respect to the table, B, with respect to the floor. So for question A, to calculate it, I used the formula Eg equals mgh and I subbed in the mass and the gravity. For the height, I subbed in 0.8 meters because you can see in the diagram, the textbook is that high above the table. Therefore, the textbook's gravitational potential energy in relation to the table is 78.5 joules. Now let's do this again with respect to the floor. We used Eg equals mgh again, subbing in the same value of mass and gravity as we did before, but for this time, the height we used 0.8 and we added 1.2 because we wanted the height from the textbook to the floor. Therefore, the textbook's gravitational potential energy in relation to the floor is 196 joules. As you can see, the textbook had a greater Eg in relation to the floor because of the height and because it's the only thing that increased in part B. But what would happen if we took the same problem but increased the mass by 50% or 5 kilograms? How would this affect the Eg in relation to the floor? So let's continue using the formula Eg equals mgh like we did in part B, except we were increasing the mass by 50%, and since 50% of the mass is 5 kilograms, I added that to the original mass of said textbook. I then subbed in gravity as 9.81, and for the height, I used the same height as I calculated in part B as it is asking in relation to the floor. Therefore, the textbook's gravitational potential energy in relation to the floor after increasing the mass by 50% is 294 joules. Now we can see that since we increased the mass by 50%, the Eg also increased by 50%, going from 196 joules to 294 joules. For the lab, me and Tarj worked together, and these are some of the screenshots of me performing the lab at the points that we chose, at the two extreme points, the equilibrium, and 2 points in between. Just another look at the physical quantities that Tarj had already shown previously, and this is the mass, angle, string length, and acceleration due to gravity used. Now that Tarj has already shown the physical quantities of the lab, let's get into the data that I gathered. I collected the height and Eg at 5 different points, the 5 points being the 2 extreme points, the equilibrium, and the 2 points in between the extreme equilibrium points. To find the height, I did L minus L cos theta, L being the length of the string, but also the hypotenuse of this right angled triangle in the diagram on the right. Using trig ratios and some concepts, we can find the heights listed in the previous slide. Theta was 0 degrees at the equilibrium, 20 degrees in between, and 40 degrees at the 2 extreme points. I use this method to get a more accurate height instead of just measuring it myself. I found Eg using the Eg equals mgh formula when the pendulum was at 0 degrees and 40 degrees using the mass 0.1 kilograms and the associated heights at these points. At 20 degrees, the pendulum had both height and speed, so there was Eg and Ek. I set up E total equals Eg plus Ek, using the value of Eg at my extreme point to be E total, since energy was purely Eg there. I used the value Tarj found for Ek to solve for Eg. Here are 2 graphs that show how height and Eg increased when the pendulum was at 20 degrees and 40 degrees. As you can see, they are both straight lines, so there is a linear relationship between Eg and height. If we use the formula, this would be the case because there are no exponents in it. Therefore, the relationship we found between Eg and height is the same as the theoretical proportionality observed in the formula.
So that concludes our presentation on how work and conservation of energy with Eg and Ek work in a simple pendulum.
Thank you for watching.